Okay, this is chapter 7. We're going to talk about how to do different kinds of hypothesis tests and confidence intervals when using multiple regression. So this will be very similar to what we did with simple linear regression, but little changes. Hypothesis tests and confidence intervals for a single coefficient in multiple regression follow the same logic and recipe as for the slope coefficient in a single regressor model. Basically, we divide the coefficient by its standard error to get the t statistic. Thus, we can test hypotheses using the usual t statistic and confidence interval construction. So, point estimate beta 1 plus or minus 1.96 if that's a 95% confidence interval times the standard error of our point estimate. And that works if we're looking at beta 2, 3, beta 4, etc. That's only looking at one coefficient holding the others fixed. So the coefficient student-to-teacher ratio in 2 is the effect on test scores, or average test score, of a unit change in student-to-teacher ratio, holding constant the percentage of English learners in the district. The coefficient on student-to-teacher ratio falls by half. So we divide our coefficient by our standard error. So negative 1.10 divided by 0.43 gives us negative 2.54. We then go look at our z-table and see that negative 2.54 correlates to, find the z-table. So you read this, negative 2.5, and we go over to here. Negative 2.54 is associated with a p-value of 0.0055, but that's only for a single-tailed test. If we're doing a two-tailed test, we're going to multiply this number by 2. So if we multiply 0.0055 times 2, we get 0.011 for our two-sided test. Both of these are less than 0.05, and thus we can reject the null hypothesis at the 5% level. What if we want to test joint hypotheses, though? Let's say we add a third variable, expenditure per pupil. We want to test whether any of the variables affect average test score. So we hold the expenditure per pupil variable fixed and analyze the effect of the other two variables. What we are really testing is that expenditure per student does not matter. To do this, our null hypothesis is that both beta 1 and beta 2 are 0, meaning they are uncorrelated to average test score. Our alternative hypothesis is that anything is not 0, basically. So that can be either beta 1 is not equal to 0, or beta 2 is not equal to 0, or both. So basically, it should be really easy to reject the null hypothesis because everything has to be equal to 0 for the null hypothesis, but as long as one thing or one coefficient does not equal 0, then we're able to reject the null hypothesis. Hopefully, if you remember analysis of variance or ANOVA, this kind of looks familiar. And you can kind of see how ANOVA and multiple regression are connected when we start looking at this particular kind of analysis. So a joint hypothesis specifies a value for 2 or more coefficients. That is, it imposes a restriction on 2 or more coefficients. In general, a joint hypothesis will involve Q restrictions in the example above, Q equals 2, and the two restrictions are beta 1 equals 0 and beta 2 equals 0. So a common sense idea is to reject either of the individual t statistics exceeds 1.96 in absolute value. But this one at a time test isn't valid. The resulting test rejects too often under the null hypothesis. So why can't we just test the coefficients one at a time? Because the rejection rate under the null isn't 5%. We'll calculate the probability of incorrectly rejecting the null using the common sense test based on the two individual t statistics. To simplify the calculation, suppose that t1 and t2 are independently distributed. This isn't true in general, just in this example. But we have to look at another metric to take care of this problem. That's when we use the F statistic, or the F statistic comes into play. The F statistic can tell us can test all parts of the joint hypothesis at once. To find the F statistic, we take our two t statistics and square them, then multiply by twice their correlation. Then we divide by 1 minus their correlation squared, and then divide by 2 to get the F statistics. Basically, what this does is it averages those two t statistics together, taking into account their correlations. That's where the rho comes in. So we reject when f is large, but how do we know how large? We use software to calculate the F statistic the majority of time because after two variables, the math just becomes too hard to do by hand. It ends up being matrix algebra. But this gives the F statistic a nice large sample approximate distribution, which is the chi-squared distribution. In large samples, the F statistic approaches the chi-square distribution. The chi-square distribution with q degrees of freedom is defined to be the distribution of the sum of q independent squared normal random variables. So with 1, it's 3.84, so if our F statistic is above that, then we can reject the null hypothesis. Same thing for when q equals 2, 3, 4, or 5. And that corresponds to the degrees of freedom with respect to the chi-squared distribution. Okay, so if we have some regression formula here, our typical regression formula, dependent variable, intercept, and each of our coefficients, what if we wanted to test a different hypothesis and whether beta 1 equals beta 2? So considering this, the null imposes a single restriction, so q equals 1 on multiple coefficients. It is not a joint hypothesis with multiple restrictions, where we compare beta 1 equals 0 and beta 2 equals 0. In order to test this hypothesis, there are two ways we can do it. Here are two methods for testing single restrictions on multiple coefficients. First way, we can rearrange or transform the regression. Rearrange the regressor so that the restriction becomes a restriction on a single coefficient in an equivalent regression. Or we can perform the test directly using some software. We can use R to do this, but R will let you test restrictions using multiple coefficients directly. So the first method is to transform the regression formula. So we have to substitute a function that allows us to test what we want. Basically, we have to add and subtract beta 2 and x1 from each of the terms. So we subtract beta 2 from the first term and add x1 to the second term. What we are trying to create is a term where beta 1 minus beta 2 exists, which is equivalent to beta 1 equals beta 2. So we want to create this from our regression formula. So by subtracting beta 2 from this first term, we get beta 1 minus beta 2. But in order to do that, we have to add x1 to the second term. And thus, we get our beta 1 minus beta 2, which if we substitute a variable to cover that, we have our new regression that we can run, and then we will find the coefficient for this one will give us the answer we're looking for. However, that's overly complicated, and we can do it similarly in R. So basically, with transforming, we're changing our null hypothesis then to be equal to 0. In R, we can test it directly. So to do this, we can run our regression the way we normally do. So the easier way is to just use software. In R, we can run our linear model as usual and then do a linear hypothesis test. This function comes from the car package in R, so you have to install that package in library to run this test. So let's look at R real quick. In this updated script, I've brought in the new expenditure per pupil variable. We can look at the data over here. So we have average test score, student-teacher ratio, expenditure per pupil, and percent of English learners. So if we run our model, let me clear all this out. Our regular model, we get our estimates, our homoscedastic standard errors. We have to run a different command if we want our robust standard errors. We get our F statistic, which is pretty high, and thus our model is statistically significant. But if we run a linear hypothesis, we can test whether S, or our student-to-teacher ratio, is equal to our expenditure per pupil. So it runs it, and we get our F statistic for that, as well as our p-value, and it is statistically significant. And thus we can reject the null hypothesis that those two values are equal, because obviously they're not equal. And so a 95% joint confidence set is a set valued function of the data that contains the true coefficients in a 95% of hypothetical repeated samples. Equivalently, the set of coefficient values that cannot be rejected at the 5% significance level. You can find a 95% confidence set as the set of beta 1, beta 2 that cannot be rejected at the 5% level using an F-test. Something important to note is when there are two coefficients, then the resulting confidence sets are ellipses. This is a question on our homework, so something worth remembering. Lastly, we want to decide on which variables to include in our regression. Our first step is to identify the variable of interest. In our California schools data, we're interested in the students' average test scores. So we thought that maybe the student-to-teacher ratio is a determinant of average test scores. Next, we have to think of possible omitted variable bias. We need to include those variables if possible, such as percent of English learners, or find possible control variables to account for the variance associated with the omitted variables. So try to think of as many as possible alternative variables that could be causing the effect you are hypothesizing with your model. Then we have to create alternative models to show the robustness of your analysis. Then finally, do sensitivity checks, such as does a candidate variable change the coefficient of interest? Is a candidate variable statistically significant? But don't just try to maximize R squared, because like we've talked about before, just adding variables increases your R squared, but you may actually be improving your analysis. So analysis of the test score data set. If we identify the variable of interest, so we said student-to-teacher ratio, then we think of the omitted causal effects that could result in omitted variable bias. So whether the students know English, the variable we collected on percent of English learners, outside learning opportunities, parental involvement, teacher quality, teacher salary is correlated with district wealth. There's a long list of possible variables that can be associated with this particular variable of interest. So we include those omitted causal effects if possible, or you try to develop control variables to mitigate the omitted variable bias. The control variables are effective if the conditional mean independence assumption plausibility holds. So if our error term U is uncorrelated with student to teacher ratio once the control variables are included. This results in a base or a benchmark model. Many of the omitted causal variables are hard to measure, so we need to find control variables. These include percent of English learners, both the control variable and an omitted causal factor, and measures of district wealth. Also, specify a range of plausible alternative models, which include additional candidate variables. It isn't clear which of the income-related variables will best control for the many omitted causal factors, such as outside learning opportunities. So the alternative specs include regressions with different income variables. The alternative specifications considered here are just a starting point, not the final word. Finally, estimate your base model and plausible alternative specifications and do the sensitivity checks. So to summarize with multiple regression over the chapter 6 and 7, multiple regression allows us to estimate the effect on y of a change in x1 holding other variables constant. You can measure a variable, you can avoid omitted variable bias by including it in your regression analysis. If you can't measure it, then you might need to control for it using some variable that is correlated with the omitted variable and the one your included variable. There's no simple recipe for deciding which variables belong in a regression. There are other advanced techniques that I don't think we'll get to in this class, but we'll talk about in other classes of how you can select variables using really advanced machine learning algorithms. One approach is to specify a base model and then add to it and see how the estimates change for the variable of interest. So, best of luck.